steady state error is a function of input. That means type of input we have, whether we will be having a ramp input, whether we will be having a step input, whether we will be having a parabolic input. So any type of input. So input, it's a function of input transform, and then it's also a function of transfer function. So two things are very clear. So steady state error is a function of input transform and transfer function. So it should be very clear. So two things it will depend on, input transform and transfer function. So I can write down ESS, steady state, function of input transform, and then we write it transfer function or G of S. Two clear things, two things we have to see. Now from this expression, today we are going to deduce some more expressions. There are three terms, namely position error coefficient, then we have velocity error coefficient, and then we have acceleration error coefficient. And the respective inputs which we will give to all those three quantities will be a step input, will be a ramp input, and will be a parabolic input. Step input, in the meantime when we deduce the expressions, will be termed as step input, will be also termed as position input, and correspondingly ramp input will be termed as velocity input, and then subsequently last input, that is the parabolic input, will be termed as acceleration input. So these are very important from the examination point of view. Okay, let's start. Okay, right now let's consider the different cases. Let's consider the different cases when a system is subjected to various types of inputs. Subjected to various types of input. So this expression will be considered as a reference expression which we have already derived. Now case number one, when your input will be a step input. That is, step input means R of t will be equal to U of t. Then we are going to take the Laplace transform of that. U of t Laplace transform is 1 by s. And once we will substitute that value of 1 by s as R of s, then we will define a term called a position coefficient. Okay, position error coefficient term from this. And then we are going to see what will be the steady state error. So number one, case number one. Case number one, when U of t will be, R of t, that's the time domain input will be U of t. Then taking the Laplace transform of this, R of s is equal to 1 by s. So substituting that expression in the steady state error or E of infinity, which is in case of a step input, then we can say limit s tends to 0 as R of s in Laplace transform is 1 by s plus 1 plus g of s. Now this term will get cancelled. S tends to 0, that will be 1 plus 1 by g of s. Now in this case, limit there is a term called limit s tends to 0 g of s, because 1 is a constant, and if s tends to 0 it will not have any type of influence, it's a constant. So this term, we will call this term as Kp, and this is called as term Kp. That term you can write, it's called position error coefficient term. Position error coefficient, and then steady state error, or the infinity, is steady state in this case will be, this is position error. We have defined the term Kp is equal to limit s tends to 0 g of s. So from this we can reduce the steady state error for a step input as, okay, that can be termed as 1 divided by 1 plus k. So if we have to find the steady state error with an input of step, then this is the right expression. So Kp we can write down as position error coefficient. We have defined from this, because 1 will not have any influence. S tends to 0, it's a constant. So what will have an influence? That is a g of s, it's a transfer function. Transfer function may involve poles, zeros, poles on the origin, on the real axis, blah blah blah. So that will definitely have an influence. So that is termed as a position error coefficient. Next, case number 2. Case number 2 is when R of t is equal to tu of t. We also call it this, we call it, write down here, step input, and this is called a ramp input. Now in this case again, using the expression number 1, the steady state error, that is a E ram infinite, or E at steady state will be equal to, sorry, we can take the Laplace transform on this. Taking the Laplace transform, R of s will be 1 by s square. So this is limit s tends to 0 okay, then that will be s into 1 by s square, that will be 1 plus g of s and s gets cancelled, so E ram at steady state will be limit s tends to 0, that will be 1 by s plus s into g of s. Now if you approach the limits, s will term as 0, it will be 0, so this will remain as g of s, limit s tends to 0. We cannot say, here I am writing for your explanation or for your clarification, this term cannot be equal to 0. Why? Because we don't know what is the behavior of this transfer function. This transfer function can have a pole at origin, this can have a pole at 0 at origin, so we don't know the behavior of this one. So this term cannot be termed as 0. So we are writing this term like this. Have you understood or not? 1 by s g of s. Somebody may be thinking, sir, s को 0 कर दूं क्या हो गया? लेकिन s को 0 करना इतना आसान नहीं है. Maybe the term will be s 1 by s plus 2, s plus 3. Transfer function will get cancelled. So we don't know the behavior of the transfer function. That's why we cannot say that this term will be equal to 0. So from this term, another term, kv we can take, kv term we can write, kv will equal to limit s tends to 0, s g of s, okay, and that term is called velocity error coefficient. have to find the error at the steady state. That means when the input is RAM, ESS will be 1 by KB. So this thing you have to remember. I hope this is clear. Why are you so astonished? Fine. Number third. Now let's consider the third cases. Case number third is when R of t is 1 by 2. Okay? I think standard we write 1 of 2 u of t. For this one. 1 by 2 t u of t. This is a standard term. You sometimes manipulate it. If 2 is t u of t is there, this should be square. T square u of t, but half is there. That's a standard. So sometimes half is not given. T u of t square u of t. You have to manipulate it, multiply by 2 and divide by 2. That manipulation has to be done. The standard term is half of t square u of t. Then if you take the Laplace transform of same, the Laplace transform will be 1 by s cube. So substituting the same E parabola for steady state, this will be ESS at the steady state limit s tends to 0. And the equation number 1, s will be 1 by s cube divided by 1 plus g of s. Okay. Square and cube will get cancelled. So E parabola at steady state will be limit s tends to 0. Then this will be 1 by s square plus s square of g of s. Now we will approach the limits. This will be 0, but this term again with the same explanation cannot be equal to 0. Why? Because we don't know what is the behavior of the transfer function. It can have 2 poles at the origin, 2 poles at the 3 poles of the origin. Nobody knows it. So we don't know the behavior of this. This term cannot be termed as 0. Yeah, thank you. So this term, this cannot be termed as 0 because that will entirely depend on the behavior of this transfer function. So we don't know that. So hence this cannot be 0. So another term will come into the picture, that is KA. That should be equal to limit s tends to 0 s square of g of s, which is nothing but, which is velocity, sorry, which is acceleration, error coefficient. Hence, error, if we have an error at a steady state, in case when the input will be parabola, so that should be equal to 1 by Ka. You have to remember this. This term is for the error, and this is the quantity for the position error coefficient, position velocity coefficient, sorry, velocity coefficient, and third is acceleration error coefficient. 3 terms will be there. Now sometimes this input here, ramp input, is also termed as input. Another name given to this, sorry, step input is given as position. So sometimes some literature, some books in the literature will write position input. And for this, they will write as velocity input. And for this, they will write as, this is a parabola input. They will write as an acceleration. Okay. You will also take some time for transition to online to offline. Okay. These terms are used for. These terms are used for what? These are used for acceleration, velocity, and so this is basic about that. So let's move to the next. I hope this is clear. So what is an acceleration error coefficient? S square, limit s tends to 0, s square g of s. And if you have to find the error at the steady state, 1 by K. What's the position error coefficient? Limit s tends to 0, g of x only. Here, g of x. Okay? And for similarly for the acceleration, limit as tends to 0, as per 0. So if you have to find the error, 1 by k. For 2, we have 1 by kv, and k for 1, I have 1 divided by 1 plus kv. This should be remembered, memorized. Okay? Next. Now let's say the behavior of input is like this. Okay, this is for the example's sake. Let me say I have an input whose behavior is like this. What's the behavior? I need to see what's the behavior. This is R of t as an input. R of t is given as u of t plus t u of t plus 1 by 2 t square u of t. Okay? Now, for this, if I have to write steady state error, Shabash, rule number 6. Directly I have to write steady state error. ESS will be given as 1 upon 1 plus kb plus 1 divided by kb plus, that's all, finished. We don't need to do anything, but we know what should be the value of kp, kv and k. Management आपको समझ आ रहा है? You are getting it at the end? You are able to understand or not? If you have any queries, you can always do. Next, another type of input I have. This is a complete input. Another type of input is what that input? Let me write it. A, I think this is the same, I know. B, T u of t, and then I have C, T square u of t. Tanzil, what has to be manipulated in this case? You have to bring them in the standard form. So divide out. This further can be written as the other one. A u of t plus b u of t. Now here we need to what? Multiply and divide by 2. This is the standard form of the input. Then, if I have to write a steady state error for the same, so steady state error in this case is given as ESS. ESS always means peak infinity. That's very clear. Steady state means infinity. I have seen last time on question. So this should be A divided by 1 plus kb. This should be B divided by kb. This should be 2c divided by k. That's all. Clear? Okay. Now let's see another. We have an open loop transfer function. Let's see what is the behavior of this in the 3 cases. I'll be explaining them in the detail, but at the end of the day, you have to remember the conclusions, so that there is a competitive exam. You don't have to think. You don't have to think. You don't have to solve it. You memorize the results on the basis of the last conclusion. You can easily take the correct option. This is for the sake of the competitive, particularly grade examination. Next, let us see the behavior of the open loop transfer function. Now, what's the open loop transfer function? Yourself. Fast, a time नहीं होता है. What's an open loop transfer function? हाँ? हाँ?
ओपन लूप पता है नहीं, क्लोज लूप पता है.
क्यों नहीं पता है? You are sleeping that time? ठीक है? जो absent थे, please make sure that attendance will be taken into account. आप कहाँ सोए हो? ओपन लूप तो मैंने clearly explain किया है. Yourself, what is an open loop transfer function? loop transfer function. Let's see how we can analyze the open loop transfer. ये जो मैं दिखा रहा हूँ, these are very important things. ये book में इतने अच्छी तरह analyze नहीं किया होगा. Okay? So this is very important from every examination point of view. Why I am explaining? I have explained them in the detail. Yeah. Okay. Then what you have to conclude them and then you have to remember. It's not difficult to memorize. Behavior of an open loop transfer function. Consider a confined. यूनिवर्सिटी ने दिए क्योंकि जब ये यूज नहीं होते तो फिर दिमाग में भी जंग लग जाता है, सब जंग लग जाता है. Okay, let's see the behavior. Behavior is very important. Not to conclude. We have to conclude something. So let me write a general transfer function. Open loop. G of Hs is an open loop transfer function, but I am not writing Hs. That means what? It's a unity with a unity feedback. Feedback is unity. That's very clear. Okay, G of S I am writing K dash S plus Z1, S plus Z2, S plus Z3, so on and so forth up to S plus Z1. Then what I am writing here, S is called N, S plus P1, S plus P2, S plus P3, S plus Pn. Whatever he has equivalent to get, but this is the form. Now what is this capital N? Capital N, what is this capital N? Roll number 6, Johan? What degree? I have told you, this is number of poles at the origin. And a capital N to the origin. I am talking about this thing. If it will be one number of poles or zeros, I think I have explained the poles and zeros. So if N is defined here as number of poles at the origin. Okay, so you can write down capital N is number of poles at origin. Rest all terminologies are same. Z1 is what? Number of zeros. So P1 is number of poles, and then last term N I am going to define. Z1 तो आपको पता ही है number of zeros हम करें. Z1 number of zeros. P1 up to so on and so forth. Yeah, Z है number of poles. And N I am again going to define. Okay, N although is the number of poles at the origin, but the degree N is also important. Another thing. Now degree N says it's a type of a system. Degree N, the value of N will also the value of N can we can say that value of N will also define the type of the system. It can define whether it's an open loop system, whether it's a closed loop system. So type of system, type of open loop system, type of closed loop system. That I am going to explain later. So type of system. Next is type of open loop system, type of closed loop. Another say that we will say it's a transfer function. When we talk about a system, you are not going to write a system, write it like this. दोनों एक ही बात है. Over TF. Let's see how we can say that. Closed loop system, open loop system, and type of system. Now, if n will be 0 in this case, then we will see that's a type 0 system. If n will be 1, that will be type 1 system. If n will be 2, that will be type 2 system, so on and so forth. So let's take, now let's consider again the different cases, and then we can. Case number 1. If n is equal to 0, then this, when n will be equal to 0, so this system will be type 0 system. This is 0, type 0 system. Okay? Now what we have to see in this type 0 system? It's an open loop transfer function, then open loop transfer function as is for n, then this should be 0, that is type 0 system, it should be 0. Anything raised power 0 will be 1, but the value of n has to be 0. It's an open loop transfer function where the feedback is not there, there's a unity feedback, but when I'm defining this is an open loop transfer function, nobody can deny this. As raised power n, yes, we have to see what's the degree of n. Degree of value of n is 0, anything raised power 0 is 1, so there will be no pole at the origin in case of type 0 system. It's very clear. Are you getting me or not? I'm repeating again. If I am considering first system, n will be 0, type 0 system. Now this is an open loop transfer function, and h of s is 1. G of s, h of s is an open loop transfer function. Then, in case of open loop transfer function, how I define it? I have to define the degree of this suffix, that is degree of this constant n, that should be 0. If this is 0, anything raised power 0 is 1. This is becoming n equal to 0, and this is becoming n equal to 0. That clearly specifies that in case of a type 0 system, there will be no pole at origin. There will be no pole at the origin. Okay. If there is no pole at the origin, then what is going to happen? Let us say first a part for this. Let's say input is unit step. Okay. If the input is unit step, and I don't need to write now Laplace transform of same is 1 by s, that everybody knows. So what will give it g of s now? G of s will be k dash s plus z1, s plus z2, so on and so forth, s plus zm. Okay. Then we have s raised power 0, then s plus p1, s plus p2, so on and so forth, s plus pn. This further can be written as g of s can be written as k dash s plus z1 plus s plus z2. I'm explaining this in the detail. Next, I'm not going to explain like this. Again, this will be 0. Because things should be understood later. So up to here, I think it's very clear. I have nothing else. I've used the term type 1 system. We have just used the n equal to 0. Now what I am trying to get? I will try to get the two things. Number one will be the steady state error. In this case, when I will get the steady state error, I want to see what should be the value of the steady state error. Now for the steady state error, if I am taking this as an input, then Kp term is used here. Kp term is limit s tends to 0 g of s. Okay. This is what? This is position error coefficient. I am writing again just so that you can remember it. Okay, then if I am talking about the steady state error in this case, then it is equal to 1 plus Kp. s tends to 0. Okay, what is g of s now? Now you can see g of s is this complete. I will write g of s only, I don't write the complete term. Now if I put s is equal to 0, so everything s will be 0. So term will become k dash, it will become z1, z2 and so on and so forth up to zm. Then it will be divided by p1, p2, so on and so forth up to pn. Let's say this whole term will be all are constants. So this will be equal to some value, that's a constant k. Some value, that's a constant k. So steady state error in this case is ESS when we have a ramp input will be 1 upon 1 plus k, and definitely this is going to be a finite value. So what we conclude first? We conclude that in type 0 system, if input is unit step, then what happens? The steady state error which we obtain in any case, steady state error which we obtain will be having some finite value. That will be, it will definitely have some value. Okay, let's move further. Second, B. Now let me change the input. R of t is what? Tu of t, that you already know. That's a ramp input, also called velocity input. And if I take the Laplace transform of this is 1 by s square. Okay. Now, if I am going to substitute the same value here, so before substituting, let me clear some terms. I know this term kV is limit s tends to 0 s g of s, that is called velocity error coefficient. And then if I have to find a steady state error whenever the input is ramp input, then I have to write it like this, kV. There is no question in this case, already explained. Okay. Now further, kV, that is velocity error coefficient, will be equal to limit s tends to 0 s, okay, into g of s. So what is g of s now? G of s is all this k, whatever there is. I am not worried about this g of s. This is g of s. So whenever it will tend to 0, it will become 0. kV will become 0. So in this case, what is going to happen? Steady state error will be 1 by 0, that is infinite. So whenever type 0 system will be having ramp as an input, then in that case steady state error will be always infinite. Okay, let's move to the case number 3rd. Case number 3rd is when you have R of t equal to 1 by t square u of t. That is clearly here. This is infinite. Error is a parabolic input. And in this case, what will happen? Laplace transform of this is 1 by s cube. Okay? Okay? So, in that case, what will be the term? Term will be Ka. K will be defined as limit s tends to 0 s square g of s. Okay? And that g of s will be, this is called acceleration error, coefficient. Now, if I have to find the steady state error, that will be 1 by Ka. Now here, Ka will be limit s tends to 0. So whatever the GS is there, what whatever the value of gs is there, s will be multiplied by that, and that should be again equal to, okay? I think लिखने की जरूरत नहीं है, वो नीचे आ जाएगा. तो if you are writing gs, maybe you are confused because of this. Let's write a gs. You have to type explain नहीं किया है ना, type 1 ही है. This is type 0, sorry, type 0, type 0, type 0, type 0. इसमें कंफ्यूज होने की कोई बात नहीं, why you are confused? ठीक है ना? As I am not writing because this is 0. So this will be 1. So no need to write it. That's why I am writing directly. maybe आप देख रहे हैं सर क्या हो रहा है. So whatever is here, s is not involved. So you multiply this, it will be 0. And this will be 0. Then steady state error is 1 by 0, that is infinite. So very clearly in a type 0 system, whenever the input is unit step, you will have a finite value. Otherwise, steady state error is infinite. Let's move to the second. इसी से manipulate करते हैं सबको. I hope first you understood. Can we manipulate this now? I think we can manipulate. Now these are same. Case number 2. Case number 2, what's happening? N will be equal to 1. Type will be, okay. So S will be there in the denominator. So case number 1, this is the same thing. S will be there in the denominator. Now Kp will be g of s, and have a look here. Okay. So Kp will be into g of s. So when we will substitute the g of s equal to, we can substitute it. Okay, no problem. So now we are having s fine. So whenever we are having s, g of s is this complete. So this will be 0. ठीक है? होगा ना 0. यहाँ 0 आ जाएगा. So when this will be 0 at the denominator, then Kp will be what? Infinity. So we have Kp value here as. Is it clear or not? ये जो फंक्शन है इसमें क्या आ रहा है? g of s is equal to what? g of s, we have substituted this value 1 is coming here, fine. 1 has came here, okay. Now position error coefficient will become limit s tends to 0, g of s has 1 in the denominator. 1 in the denominator means, sorry, s in the denominator. That means 1, s value is 0, 1 by 0. Whatever is on the other side, we are not worried. 1 by 0 is what? Infinite. So if we talk about the steady state error of this one, steady state error of 1 by infinite. 1 by infinite is 0. Okay? So here, you don't have to write this. This was for the earlier case. Is it clear? Okay. This is for your type 1 system. The steady state error is 0. समझ आ रहा है? Case number 2. याद ही लिख लेना, ये फाइनल. Now this is RAM. This is defined as what? Velocity error coefficient. Okay. Now here it will be s g of s. Let me take off this. Okay. This will be 0. Okay. Now here, what will be the value of this? S, g of s is 1 by s. है ना, 1 by s कैंसिल हो जाएगा, लिखने की जरूरत है, you can calculate that 1 by s will get cancelled, left over will be this one. So if I talk about this is k, z1, z2, zm. Similarly we have p1, p2, pm. Let's say this is again equal to some constant. So steady state error in case of which input? We are talking about the ramp input. It will be 1 by kV. So this is some value. Steady state value is 1 by kV. That is 1 by kV. That is some. This is a finite value. K dash whatever you want, right? Finite value. समझ आ रहा है कि नहीं? This is a finite value. Type 1, yes. Finite. Okay, move to the third now. Same input, parabolic input, acceleration coefficient. So here what will be? K A will be s square into g of s. G of s will have a denominator s. One of the s will get cancelled. So still it is going to remain s into g of s. Is it clear? Limit s tends to 0. So limit s tends to 0. So whatever the case may be, this is going to become 0. So k is going to become 0. So again, if k is going to become 0, so 1 by 0 is infinite. So what is happening in type 1 system? Type 1 system, what was first case? We got 0 here. Type 1 system, only the finite value will be obtained whenever the input will be unit. Which one? Ramp. See now third. This is going 1 by 1. 0 in type 0 system, finite value will have which? Unit step. In type 1 system, finite value will have ramp. In type 2 system, you can say finite value will be having ramp. So this is the pattern we will be getting. Now let us say again, consider the system. N is 2, type is 2. Okay? I don't think this is a rocket science. You can do at your leisure time also. कोई values लगानी है, खाली एक मैंने अच्छी तरह बताया, बाकी. So this is s square and this is n is 2. Roll number 6. What is going to happen here now? Kp is s, g of s. Now g of s will be having a value of square. So 1 by 0 will again become infinite. So ASS 1 plus infinite will become 0. This will not have any change. Okay. Number 2. Same as g of s. So what is going to happen here? S g of s. Okay. S g of s. G of s is having square now. One of that will get cancelled. Is it clear? S g of s. So this is will be 1 by g of s is 1 square. So s and that will get cancelled. So we will be having something. S will be in the denominator. S will be in the denominator. 1 by 0 is infinite. So here 1 by infinity is it clear or not? 1 by infinity is 0. So steady state error here will be 0. Now consider the third case. Same, s square g of s, acceleration coefficient. Okay, s square and that is going to get cancelled. G of s. Limit s tends to 0. Only g of s will be left. So that is what g of s will be. What? Again the multiplication of all those terms. K dash because s is 0, z1, z2, so on and so forth. Zm, and then this is P1, P2, so on and so forth up to Pn, and this is, let us say, constant K. If this is a constant K, then steady state error will be 1 by K. It's again something like constant K double dash, whatever you see. So this is again a finite value. So it should be very clear that whenever the input is unit parabola and the system is type 2 system, then only we are going to get a finite value in type 2. So what we conclude from all these things, okay, what we conclude for all these things. Let me put a summary that I have a type here and I have a system here. Sorry, I have a type here and I have an input. Type is what? Type is what? 0. And input is what? Step. I hope this is clear. Anybody has a question? We can raise the question. You can raise this question. थोड़ा मैंने दो को मैंने जल्दी किया है because there is no question in solving all those things because we have already done the types of the system. We have explained everything in the types of the system. You have to just know the mathematical values. That's all. Okay. Now what we can conclude from this, number one, if we have type of system and we have then type of input also. From 0, 1 and 2. High unit expression 2 is enough for us. Okay. Input is u of t. Input is t u of t. Input is half t square u of t. So this clearly is unit step, also known as position input. This is unit ramp, also known as velocity input. This is unit parabola, also known as acceleration input. Now these are corresponding things. 0 corresponds to step input, 1 corresponds to this. Now, if the order of the system and the order of the input are same, then the steady state error is finite. This is the order, this is the input. If the order, we need it now. Let me conclude. If the order of the system and the order of the input, applied input is same, this is the order I am writing. अपना order लिखोगे फिर कहोगे सर ने ये कहा, that cannot be entertained. Okay? This is the order I am writing. If the order of the input and the type of the input, type of the system and the order of the input are same, then we will always get a steady state error will be a finite. Steady state error is finite here. Steady state error is finite here. If type of the system is greater than the input of this is greater than the input type of the input, then steady state error will not be finite. Okay? Then the steady state error will not be. So these 2 points you conclude. If the order of the input is same, if order of the input is same as the type of the system, then the steady state error is finite. If the order of the input is same and the type of the system, then the steady state error is finite. If the order of the input is greater than the type of the system, if the order of the input is greater than the type of the system, then the steady state error is infinite. तीसरा भी conclusion है इसका. Second is if the order of the input is greater than the type of the system, the steady state error is infinite. तीसरा है if the type of the system is greater than the order of the input, if the type of the system is greater than the order of the input, the steady state error is 0. will be 0. Of course, these results will be valid for what? Negative feedback unity control system, which we are talking about. Negative feedback unity control system. Okay. So this was something about product. Okay, now next analysis is steady state error of non-unity feedback. See, before going to this lecture and before going to this topic, let me very clearly specify this that most of the books are wrong in this case. In case of a non-unity feedback, what they are doing, particularly the local books which you will be doing, what they are doing, they are converting the non-unity feedback to the unity feedback and then finding the error. That's not the right approach. If you have to find the right approach, there is a book called Automatic Control System by B.C. Koo. He has given the complete details, and I have seen it from there. There was a discrepancy in 2014 regarding this. IIT has framed a question about, first time they have framed a question about the non-unity feedback. The answer was wrong. They thought the marks were given to everyone. So students were at the end of the day happy because the answer was wrong. That should not be in the answer. Whatever the approach you have to follow, you don't have to convert a non-unity feedback into the unity feedback. That's not the right approach. But something different is the approach for finding the steady state error. So let's see how we can do it. Okay, next is analysis of steady state error. Later on we'll go for the different questions. There are very good questions from the GATE examination, so we'll see those various questions. Even an IIT professor can do a mistake, there's no problem. But he is also a human, but he also can. Okay. The next is analysis of a steady state error for non-unity feedback system. So let me draw a non-unity feedback system. Transform domain it is. This is my input R of S. This is G of S. Of course, the negative feedback, there is definitely. It's not a unity feedback. Non-unity feedback, we are getting HFS here. Now, normally, what is our approach in a unity feedback? Let me explain that first. Normal approach for us is that we have an input and then we have a transfer function, we have output, and then we have a unity feedback. This output is same here, so this we are getting here, and then when I am getting an error is input minus output, and in time domain it is R of t minus c. So this is the convention normal approach, so that's right. Because what we are getting, we are giving an input to a system. We are processing that system. We have a transfer function here. Analysis of the transfer function is done. Whatever process we are doing, we are getting output. We don't have any feedback. We have non-unity feedback. We don't have any feedback. We can take exactly the same same output from here and find that. No problem in this case. So that's a perfect way to find it now. Now here what some of the books or some of the authors, what they are doing, they are taking this input here, or the output here, multiplying this as we multiply this is C of S, H of S, then finding an error here, input R of S minus C of S, H of S, which is completely wrong. Now why it is completely wrong? Why it is completely wrong? Because you can compare the like quantities. You can compare the same quantities. If there are same quantities, let's say I have green apples. Let's say they are delicious apples. I don't think delicious are green, they are red. So, for the sake of example, because a Kashmiri person should not write this. So, red apples are delicious apples. And then, let's say we have another type of apples, they are green. But they are apples. In terms of taste, in terms of quality, in terms of flavor, in terms of other ingredients, we can compare. Like quantities are there, we can compare. But if I take an apple and I am going to compare an apple with a mango, that doesn't make any sense. Mango has a different structure, different ingredients, different taste, different climatic conditions to sustain, whereas the apple has a different things to sustain. So we can't compare an apple with orange. That's a common example in English. Here what we are doing, we are having an input, then let's say here at this end we have 1 by S, it's an integrator. So what we are doing, we are taking an output, we are integrating that output, and we are integrating that output, this entire domain, we are integrating that output. Then when we are finding the error, we are finding the error input minus the integrated output. So this is apples and oranges. Basically what we are doing, we are comparing apples with oranges. We are taking an output here. Let's say that's an integrator. We are multiplying that basically we are taking the integrative of the output. Integration of the output we are taking. We are not taking the exact output. So we are taking the integration of the output. Then when we reach here, that's an integrated output. We are finding an error between an input and the integrated output, which we do not have to find, but error definition is we have to find an error between an input and exclusively output. So this is a bigger mistake. But most of the books are doing. Let's say we have a derivative also. See, we have d by dt. Now again we are differentiating the output, taking the differentiated output to this here to the error detector, and differentiated output we are subtracting from the input, and then we are saying that it's error. That's completely wrong. That cannot be compared. These are two different quantities and two different things that cannot be compared, and we cannot find an error because of this. So what we have to do, what Q has done, we have done nothing. Okay, we'll continue this. What Q has basically done, he has given an expression in terms of error. He has told, fine, we don't have a problem with input, but this quantity has to be multiplied by something. If you multiply this quantity by something, that is which we are getting here as an output, k into h of s, and then the same constant you have to multiply by error, then it can satisfy that we are comparing both quantities. Then the comparison of the